business.
I have a quick question, actually.
Yeah.
So I was really busy the last week when we were supposed to come pick up our midterms.
Yes.
How do you want me to go about picking up my midterm?
Were you coming in like on Friday or Monday at all?
I can.
Just send me an email beforehand, like saying that you're coming in, and I'll grab it from upstairs.
All right, thank you.
Okay. So when you're coming in, just let me know, and then I will grab it.
Yeah, it doesn't matter. What I've noticed so far, it doesn't matter if it's a Georgia or Bulldog day. You can just come in.
Yeah. you can just come. Except for the midterm day.
Yeah, I'll come on my actual day.
Yeah, come on the actual day for the midterm.
Also, I have a question that isn't really related to this class, but
Okay.
kind of. So I'm a CS major and I want to like work in AI.
Okay.
So I spend a lot of time researching like what it is to do with AI,
Uh-huh.
and it has a very heavy like linear algebra base.
Mhm.
Is it possible I can ask you any questions that I have like about linear algebra when it comes to AI?
Maybe, I don't know if I can answer them necessarily.
Because so far with what I've been studying, I've seen a lot of like reoccurring things that have happened in this class. But some things when I actually get into application of it,
Right.
kind of get a bit hazy. So if you have any questions, I can just shoot you an email. Or
Sure,
something.
yeah, I can try, you know.
Yeah,
I have to
it's
know
better
the-
than nothing.
I have to know the context, so, you know. So do you have a course in this at all?
I'm actually a freshman, so
Okay.
I am currently only surface level of the courses, but during high school, we had my high school simple directed study where we could pick what we wanted to learn.
Oh, great.
And that's when I decided to sit research. So I got all that from there.
Yeah, I mean, linear algebra is everywhere. I mean, it's computer science, mathematics, economics. I mean, it's one of the really, basic tools that we have to actually, accomplish things.
And this is the reason I took this class over Calc 3,
Yeah.
because I had these two options.
Right.
I took this class instead, so I wanted to jump right into it.
Yes. All right, let's see. How many people do we got? I see 6 so far. Probably need more. Yeah, the online attendance has been pretty good.
Yeah, I want to say that I'm usually in the Zoom,
Yeah.
but occasionally, like the past week, I was so busy to attend any lecture, and over the weekend, I just watched all of them caught up.
Yeah. So the YouTube is working for them?
Yeah, so far, because what happened with Monday kind of off through my schedule, so I had to catch up this weekend, but it worked out pretty well, and I got all the information down.
How does it compare to, do you have anything on control at all? I've never really gotten it to work.
Now, all of my stuff is through Zoom or ELC.
Oh, but I mean, in terms of the actual video watching.
I think I have one class that uses it, but it's like embedded into her ELC.
Okay.
So I just click on her ELC like links,
Okay.
and the video just pops up for me.
Oh, okay.
I'm not sure how she got it to work, but it works pretty well.
Oh, okay.
Like for the YouTube, because YouTube, sometimes it gets really finicky if I try to watch something on my phone or something.
Yeah.
But if it's on YouTube, I can pull up a math lecture on my phone and just listen to it if I'm doing something else.
Okay, good. Yeah, I know people have been having troubles with Victoria. I just wanted to make sure that, there are not any issues. And people said that you make a YouTube channel, then there's usually no problems.
Yeah, I really like YouTube, and it allows me to actually find the time easier.
Yeah, good. Okay, that's good. I just all good to know. Let's see how we're doing. Good. Okay, let's do a quick sound check. If someone on the other end on Zoom can just say something.
Hello.
A little bit louder, please.
Hello.
Okay, that sounds all right. Let me jack up the volume slightly. Okay, I think we should be all right. Can you hear me on the other end?
Yes.
Okay, good. I can hear you pretty well too. So. All right, so today, let me just remind you of a few things. So we have midterm 2. And let's see, so the Bulldogs will go first. And that's on Wednesday. Let me see, let me get the date. Let's see, maybe I can just pull it up here. Okay, so that's in week 11 up here, and it's on the 4th of November. Okay, so the Wednesday is the 4th, the Friday is the 6th. Okay, so Wednesday, 11/4. Okay, so if you're a Bulldog, you're going to take the midterm on Wednesday, November 4th. And the Georgias are on Friday, November 6th. Okay? And then there'll be 2 review sessions, the Monday before and then the Wednesday prior to that. So there'll be 2 review sessions. Okay, any questions on this? All right, so let's start back in on eigenvalues. And eigenvectors. All right, so let me introduce the idea again. So A is an n by n matrix. Okay, so you're always working with the square matrix. An eigenvector, let's see, x not 0 is a vector such that ax is equal to lambda x for some lambda. Okay, so it's just some scalar multiple of x when I apply a to that, right? And then if ax equals lambda x equals 0 for x not equal to 0, then lambda is called an eigenvalue of A. Okay, so we're looking at this equation ax is equal to lambda x. So if we have x's which satisfy that, those are eigenvectors. If we have a lambda which satisfies that, that's an eigenvalue. Okay. All right. Now let's analyze this equation more carefully. So suppose that x is not equal to 0, all right, with ax equals lambda x. Okay. So now let's rewrite this a little bit. So this is the same thing as ax is equal to lambda times the identity times x. Okay. And then we just move this to the other side. So ax minus lambda times the identity times x is equal to 0. So I can just put the x out there like that. Oops. I have a little bit of a mistake here. Let me just clean this up. Okay. So it's a minus lambda I x equals 0. Okay. So if we have this equation here, a minus lambda ix is equal to 0, what does that say about the null space of a minus lambda I? Is it trivial or non-trivial? What do we notice about this? Are there going to be free variables or not?
No free variables?
Are you sure? So a minus lambda I, is it just going to be the 0 vector, or is it going to have more vectors than just the 0 vector in the null space? The null space is the set of all homogeneous solutions for a minus lambda I. Is there a non-trivial solution? Yes or no?
No.
X is not 0. Is there a non-trivial solution? Yes or no? I have an X which is not
I
zero.
got trivial. I got the yes.
Yes, yes. Okay, good, good. So there is a trivial, there is a non-trivial solution for a minus lambda I x equals 0. So the null space here is not equal to 0 itself. Okay? So if the null space is not equal to 0, when you've done like Gaussian elimination, what has happened? You have a free variable, all right? So when you do Gaussian elimination to a minus lambda I, okay, so this, you get something which involves something like this, but then you have a free variable. Okay, so you have a free variable. So this is your u down here. So when you have a free variable with the square matrix, what is the determinant?
0.
0, good. So hence, the determinant of a minus lambda I has to be 0. All right, good. So this turns out to be an if and only if statement. Okay, so now I can set things up. So consider, I'm going to call it PA of lambda to be equal to the determinant of a minus lambda I. Okay. So what I'm saying here is that if I have an eigenvector, then what does that say about the eigenvalue in terms of the determinant and PA of lambda? So let me say it this way. So here's a theorem. If lambda is an eigenvalue of A, this happens if and only if PA of lambda is equal to 0. Okay? And PA of lambda is a polynomial in lambda. Moreover, PA of lambda is a polynomial of degree n in lambda. All right. So I'm taking this polynomial, and in order to find eigenvalues, what should I look for with this polynomial?
The roots.
The roots. Okay. So, and the eigenvalues are the roots of PA lambda. Okay? So in order to find the eigenvalues, we just have to find the roots of this polynomial, which may or may not be so easy. All right. All right. So now, if I have an eigenvalue, I've kind of shown you how to find all the eigenvectors. So here's a second theorem. Given lambda an eigenvalue of A, the eigenvectors corresponding to lambda are given by the null space of A minus lambda I. Okay, and we actually know how to compute a basis for the null space using Gaussian elimination. Okay? Any questions on these ideas?
So basically, this would just boil down to the eigenvectors being the three columns of,
Well, you have to back substitute up. You can't just use the column.
oh yeah, you're right.
Okay.
Okay.
Yeah, that's correct. We'll do an example in a second, okay? All right. Other questions on this?
I have like maybe a clarification on something.
Yeah.
So the null space, when we do like transformations, for example, the null space only stretches or shrinks by a factor, by some factor. Is that correct?
Well, I'm not sure what you mean by stretches or shrinks. I mean, you just take a matrix and you just compute out what the homogeneous solutions are using Gaussian elimination.
Okay, I'm just gonna think about it mathematically more than geometrically.
I don't know, it's just a matrix, A minus lambda I, and you just compute the null space.
Right.
Okay, we'll do an example in a second.
Okay, I think that'll help.
Okay, good. Other questions? Okay. All right, so let's see. We're on the next page. All right, so let me do an example. Okay, so let lambda equal to 3. Okay, I given an exact number. So then it turns out that lambda is an eigenvalue of A, which equals the following matrix: 4, 2, 3, -1, 1,
-3. That's a -3. 2, 4, and a 9. Okay, let me see if I can clean this up a little bit. It's -3. Okay.
All right, so I'm actually giving you an eigenvalue for this thing. You don't have to compute the roots of the P of X, PA of X. Okay, we'll do that later. All right, so how do I find the eigenspace? So the goal now is to find the eigenvectors. And this is often called the eigenspace, corresponding to lambda equals 3. Okay. All right, so how should we proceed to do this?
First, find A minus lambda I.
Good. That's exactly what we're going to do. So first I want to find A minus 3 times the identity. Okay.
All right, so I'm taking the identity matrix and I'm multiplying it times -3. So in essence, I just take the matrix A and I subtract off 3 from the diagonal. Okay. So this is going to be 1, 2, 3. Okay, remember 4 minus 3 is 1. -1, what's the next entry?
-2.
Good. And then -3. Aha. That's good. It looks like the null space is going to be non-trivial, right? And then finally, 2, 4, what's the next one? 6. Good. All right. Everyone see how we did that? You just subtract off 3 from the diagonal. Okay. So now we want to find the null space of this matrix. Oh, it's a goof up. Let's try it again. Okay. All right, so what we do is we just use Gaussian elimination. All right, so let's row reduce. So the first one is I'm just going to multiply the first one by 1. Let's see what matrix we get here. We get 1, 2, 3. Let's just put zeros here just to be kosher here. All right. All right, so let's do this. So this is going to be a 0 here, 0 and a 0. That's good. And then what do we do next? We multiply by -2. And we get 0, 0, 0. Okay, reduce fairly fast. Okay, how many free variables do we have? 2, right? So we have 2 free variables. We have x2 and x3 being free. So x2 is s and x3 is t. Okay, so there are 2 free variables. How big is the null space in dimension?
3.
How big?
Or 2?
2. Right, it's a number of free variables. And so now we just back substitute out. So we have x1 plus 2x2 plus 3x3 is 0. So x1 plus 2s plus 3t is 0. So x1 is equal to -2s minus 3t. Okay. And then we have x1, x2, and x3. x1 is -2s minus 3t. x2 is s, x3 is t. We separate out the free variables. Okay, so with s, we got -2, 1, 0. Everybody okay with that? So with t, what vector do we get here?
-3, 0, 1.
Okay, good. All right, and s and t are real numbers. All right, so this completely describes all the eigenvectors for lambda equals 3. Of course, except the 0, we throw out the 0 vector, but basically this computes the eigenspace. Okay, so this is the eigenspace. Okay, so and then a basis, might as well say this, for the null space of A minus 3I. Well, we can just take those vectors, right? Minus 2, 1, 0 as 1, and we can take the other one, minus 3, 0, 1. Okay. All right. Any questions on how we did this? So once I give you an eigenvector, you should be able to, eigenvalue, you should be able to compute out the eigenspace corresponding to that eigenvector. Just compute out A minus lambda I, and it's null space. All right. So what I'd like to do next is I'd like to just talk about things a little bit more generally and do some examples with particular types of matrices. And then on Wednesday, we'll come back to more sort of direct computations. Okay, so the first thing I like to think about is looking at upper triangular matrices. So let A now be equal to a matrix which is upper triangular, A11, A22, ANN, and then we have stuff which could be above the diagonal, and then we have zeros under the diagonal, okay? So this is an upper triangular matrix. Okay. All right, now what I'd like to do is I'd like to consider the polynomial. So first of all, let's look at A minus lambda I. Okay? So all we do is we just subtract off lambda from the diagonal. A11 minus lambda, A22 minus lambda, ANN minus lambda. There's still the same stuff up there, and then there's 0 here. Okay. And then I want to compute out the determinant of this. So let's look at P A of x, or PA of lambda, and that's the determinant of A minus lambda I. Okay. Now, this is an upper triangular matrix. So what is the determinant of an upper triangular matrix? Down the diagonal, okay? So this is going to be equal to A11 minus lambda, A22 minus lambda, ANN minus lambda. Okay, so this is a polynomial. As you can see, it's a polynomial degree n, right, in lambda. You can multiply it out if you want, but let's not do that. But what are the roots?
When ANN equals lambda.
Yes, and A11 equals lambda. So when this is equal to 0, one of them has to be equal to AII, right? So the roots are A11, A22, ANN. There are n of them, okay? Possibly n of them. They could be, the same on the diagonal, for example. All right, so with an upper triangular matrix, the eigenvalues are just the entries along the diagonal. Okay, so let's just write that out. So for an upper or lower triangular matrix, the eigenvalues are the entries along the diagonal. Okay, so for these nice upper or lower triangular matrices, to compute eigenvalues is very easy. But if it's not upper or lower triangular, of course, it's much harder. Okay, questions on this?
When you do an actual problem, is it more worth it to turn a matrix into upper triangle or lower triangle and then find the eigenvalues? Or to just find them straight?
You can do that. You can use Gaussian elimination to find the determinant of A minus lambda I. That's certainly possible if it's big.
So the bigger it is, the more likely you want to use
Yeah,
Gaussian elimination.
that's right. Okay, so of course, let's do an example. Let A be the following matrix. 1, 6, 5, 0, 1,000, and a 1, and 0, 0, 2 here. Okay. So what are the eigenvalues of A? Okay, good. So the eigenvalues of A are 1, 1,000, and 2. Okay, just the entries along the diagonal. It's an upper triangular matrix, so you can just compute the eigenvalues very easily. Okay, other questions? All right, so let's proceed on. So let me state a theorem. We'll actually use this later on. So here's the first thing. So let A be, let's say, an m by m matrix. Okay, so that's given. Okay, so A has an inverse if and only if. Well, we know if and only if the determinant of A is not equal to 0. So that means that 0 is not an eigenvalue of A. Otherwise, determinant of A is equal to 0, right? Okay, 2. Eigenvectors corresponding to different eigenvalues. Okay, so if I have a vector from like one eigenspace and I have a vector from another eigenspace, non-zero vectors, then they have to be linearly independent. Okay, any questions on the statements of these theorems? Okay, let me give you some justification. It doesn't take very long to justify this. So if you want to call it a proof, you can call it a proof. Okay. All right, so first of all, we know that A, so let's do number 1 here. So A is invertible. This happens if and only if the determinant of A is not equal to 0. This happens if and only if the determinant of A minus 0 times the identity is not equal to 0. And this happens if and only if the null space of A minus 0 times the identity is actually equal to 0. Okay, and then this happens if and only if 0 is not an eigenvector of A. Okay, so that part's not so hard. Just use the definitions. Okay, so now for 2, we want to show that if I take eigenvectors corresponding to different eigenvalues, they're linearly independent. Okay, so let V1, V2 up to Vt be eigenvectors of A. Okay, and let's just list the corresponding eigenvalues with eigenvalues lambda 1, lambda 2 up to lambda t, and we know that they're not going to be, none of them are going to be equal to one another, right? So lambda I is not equal to lambda j unless I equals j. Okay, so none of them pair up to be equal to one another, right? Now, we want to show that these vectors are linearly independent. So we have to take a linear combination which is equal to 0 and actually show that it's actually the 0 vector. So suppose we have a linear combination C1, V1, C2, V2, plus CT, VT equals 0. Okay, so we want to show each of the CIs is actually equal to 0. All right, now what we do is we apply A to both sides. Okay, so apply A to both sides. Okay, so then I get C AV1 plus C2 AV2 plus CT AVT equals A times 0, which is 0. Okay. All right. Let me call the first equation number A up here, or maybe I should call it something else. Okay, so we used A for something. Let me call it something else. Let me call it equation G, let's say. Okay, let's see if I can make it like the official G there. It looks pretty official. Okay. All right, so this is equation G. Okay, and now I want to apply the fact that I have eigenvalues here. So this implies that C1 lambda 1 V1 plus C2 lambda 2 V2 plus CT lambda T VT is actually equal to 0. Okay, so let's call this equation, we'll call this equation B here, right? All right, so now I'm going to multiply the G equation by lambda 1. Okay, so now multiply equation G by lambda 1. Okay, so I have lambda 1 C1 V1 plus lambda 1 C2 V2 plus lambda T CT VT equals 0.
That's lambda
Okay.
1 at the end.
That last time we had the one.
Oh, it should be a lambda 1 here. Thank you. All right. And now what I'm going to do is I'm going to take, let's call this G1 here. And let's call this equation G2. Okay. So this is G1 here. Okay. All right. So now what I'm going to do is I'm going to take the B equation and G2, and then I'm going to subtract them off of each other. Okay. So I'm going to take these two equations, and I'm going to subtract. And so these two things are the same, right? And what I've done is I've just reduced the equation down. So I got, let's see. So I get C2 lambda 2 minus lambda 1 V2 plus C3 lambda 3 minus lambda 1 V3 plus CT lambda T minus lambda 1 VT. And this is equal to 0. All right. Now, notice that the left-hand side is not equal to 0 because of this condition up here. So note the left-hand side is not equal to 0 because of this condition up here. All right. And then you could just keep on repeating this process until you actually show that VT is 0. Now just repeat the process. And then this implies that like CT lambda 2 minus lambda 1 VT is 0. Okay, so that means that CT has to be 0. Okay, and then you just keep on doing this. All right. Okay, so it's a little bit complicated, but it's not too bad. You just have to use the definition of linear independence in order to show this. Okay, I don't expect you to do this proof or recreate it or whatever, I mean, on a test or anything, so. But I wanted to show you how we can use the definitions in order to actually justify these statements. Okay, any questions on this? Okay, so in the last several minutes, I'd like to look at some examples of questions. And so let's start with the first one. So let A be an n by n invertible matrix. And lambda an eigenvalue of A. And the problem is show that lambda inverse is an eigenvalue of A inverse. Okay, so because A is invertible, we know that 0 is never an eigenvalue for A. So it makes sense to talk about lambda inverse because lambda is never equal to 0. So, so first of all, what do we know? So we know that AX is equal to lambda x for some x not equal to 0. Okay, so looking at this equation, I actually want to put or do something and get A inverse into this. So what should I do? Okay, so multiply both sides by A inverse. Good. So I got A inverse AX is equal to lambda times A inverse on X. Okay, the lambda could just scoot outside. And so I get the identity times X is equal to lambda times A inverse on X. So X is equal to lambda times A inverse times X. Okay, so how do I show that lambda inverse is an eigenvalue of A inverse? What should I do next?
Move the lambda over.
Right, good. So everyone said it. So just multiply it on the other side. So hence, if I take A inverse with this particular X, this is 1 over lambda times X. And here 1 over lambda is equal to lambda minus 1. Okay, and notice that the X, this eigenvectors for lambda for A is also an eigenvector for A inverse for lambda minus 1. Okay. It's kind of an interesting fact. Right. Any questions on this? Okay, 2. Explain why an n by n matrix can have at most n eigenvalues. Okay. All right. Anyone want to take a stab at this? Okay. Let me let the Zoom people. Okay. People on Zoom, anyone want to take a stab at answering this question?
Is it something to do with the eigenvalues come from the diagonal of the matrix A?
Well, if it's upper triangular, that's true. All right. But that's kind of part of it. I mean, so how do you compute the eigenvalues? What should you look at?
Doesn't it have to do with the null space?
Well, do you compute the eigenvalues by looking at the null space, or is or do you compute the eigenvectors by computing the null space? How do you compute the eigenvalues? We haven't quite done it yet explicitly, but let's sort of go up and review, all right? So at the beginning, if you look at the first theorem, the eigenvalues are computed by looking at this polynomial, PA of x, which is the determinant of A minus lambda I, okay? So let's go back down here. Did a lot today. And so the eigenvalues are computed by looking at PA of x, P of lambda, is equal to the determinant of A minus lambda I. And you want to know about solutions of this form. Okay, now maybe you go ahead and answer the question. So why are there at most n eigenvalues?
I'm not sure if this is right, but there's only so many n solutions ways that A can actually, the determinant determinant can actually be 0.
Okay, so what do you know about PA of lambda?
That's, it has to be 0 in order for it to be an eigenvalue.
Oh, no, but just what does it look like in general? What kind of function is it?
Just a identity with a number.
It's a
Well,
polynomial.
Polynomial, right? So PA of lambda is a polynomial of degree n. All right, so it could be like a polynomial degree 3, polynomial degree 4, whatever. All right, so now what do we know about roots of polynomials of degree n?
There can only be n number roots.
Right, we can get most n distinct ones. Yeah, okay, good. So therefore, there are at most n distinct roots of PA of lambda. Hence, at most n distinct eigenvalues. Okay, does that make sense? All right, we're going to compute out PA of lambda next time. All right, so last quick question. So how are the eigenvalues of A related to the eigenvalues of a transpose? Okay, so we know this relationship between the eigenvalues of A and its inverse. So what about the transpose? Well, if you just write things out, so basically we're going to look at the roots of the determinant of A minus lambda I, right? So what do we know about the determinant of something and its transpose?
Isn't it the same?
Good. Good, it's the same. So I can just replace this by A minus lambda I transpose. And when you take the transpose of a matrix, if you're adding two things, you could just take the transpose of each one and then add them together, right? So this is the determinant of A transpose minus lambda times I transpose. But the identity transpose is just itself, right? So this is the determinant of A transpose minus lambda I, which, as our notation says, it's PA transpose times lambda. All right, conclusion.
Is it the same?
They have
Right.
the same eigenvalues.
That's right, they have the same eigenvalues. So hence, because the roots are the same, right? Hence, A and A transpose have the same eigenvalues. Great. Okay, so that concludes my lecture for today. Are there any questions on this? All right, so next time what we'll do is we'll actually compute out some eigenvalues. You can imagine it's not so easy, right? I mean, even if you have a 2x2 matrix, the roots could be what? Are they always real numbers or could they be complex numbers?
It could be complex.
Could be complex numbers, right? So you can get complex eigenvalues, not just real eigenvalues.
if you have a 3 by 3 matrix, is it so easy to find the roots of a cubic polynomial? Yes or no?
No.
Yeah, so it could be very difficult. It's not so easy. So when you think about the setup, the obstruction is actually computing the eigenvalues and finding the roots of this polynomial. And so we have to be very careful, of course, to rig the problem so you can find the roots. But in general, I mean, it's not so easy to find roots of polynomials and to find the eigenvalues, okay? Especially if your matrix is very, very big. Okay, great. So let's stop here and we will continue on Friday. Good.
Thank you, Professor.
Welcome.
So in the actual, in application, eigenvalues are just like a way to